The image on the left shows a digital multimeter. The image on the right shows an analog multimeter. Multimeter meaning it can be an ammeter. It could act as a voltmeter. It could act as an ohm meter. It could act as a capacitance meter. It just depends on where you turn the dial, right? Which setting you choose. But if it's an analog version, then its operation relies on something known as a galvanometer. So I'll explain what a galvanometer is here in just a moment. This image is a dedicated voltmeter, and yeah, it's constructed of a galvanometer. In fact, it's constructed of a galvanometer plus some other internal resistance. Now, how's that other internal resistance connected in the case of a voltmeter? It's connected in series with the galvanometer's resistance. So when I say galvanometer, what I mean is a loop of wire, here shown in this cutaway of this analog ammeter. By the way, when it comes to an ammeter, we take the galvanometer and add to it some internal resistance, but in that case the internal resistance is connected in parallel with the galvanometer. So the galvanometer's resistance is nothing more than the resistance of the length of wire that wraps around this spool. Well, in the presence of an external magnet, a loop of wire experiences a torque. That's a lesson that'll come in the next unit of study on how magnetic fields exert forces on moving electrical charges. But for now, just recognize that that loop of wire that conducts a current interacts with a magnetic field and rotates, and that's why the needle moves along this numerical scale to give some indication of the number of milliamps. Okay, so when I talk about the galvanometer, essentially it's a loop of wire in the presence of a magnetic field. That loop of wire has its own resistance, but we add more resistance in parallel with that. So let's say that that symbol for resistance represents the amount of resistance just of the loop of wire that makes this thing I call the galvanometer. Now, if we could connect another resistor, maybe we can control its value, so we'll make the symbol for variable. In parallel with the galvanometer's resistance, we'll call that the internal resistance of the meter. Then all of this right here represents an ammeter. Here's a picture of a demonstration version of a galvanometer. It's just a really large version of this, so it's obvious what it's made of. You can certainly recognize the horseshoe magnet, and so there's a north and a south pole, and you can see the loop of wire down here. That's the basis of the galvanometer. There's that needle that matches up with the numerical scale. Maybe we've got negative and positive, depending on whether the current flows clockwise or counterclockwise through the loop. Here's a schematic diagram of that whole thing. Again, there's our loop of wire. There's the needle that goes along the numerical scale. What we don't see is whether the other resistor is connected in series or connected in parallel. So if the other internal resistance was connected in, let's say, series with the resistance of this loop of wire, we might say there's some additional internal resistance plus the resistance of the galvanometer itself. And then in that case, that's how we would construct a voltmeter. So here's the point of all this. Let's say I wanted to determine what's the value of this resistance. Well, I could use Ohm's law. And so I can figure out what the resistance is if I can measure the voltage across it and the current flowing through it. So the whole idea that we say voltage is measured across gives an indication that when we use a voltmeter, we don't break the circuit open and then put the voltmeter in series with the battery and the switch and the resistor, right? Voltmeters aren't connected in series with what they're measuring because, after all, voltage does not flow through things. current is the quantity that flows through things. Voltage means difference in electric potential. So I want to know what's the electric potential on the high potential side of the resistor, what's the potential at the low potential side of the resistor. So my voltmeter is connected in parallel. If I want to know the current that flows through the resistor, well, that's the same as asking what's the amount of current that flows. The current that flows through the resistor is also the current that flows through this segment of wire, is also the current that flows through this segment of wire. It's also the current that flows through the battery. It's the same as the current that flows through the switch, right? There's only one amount of current that flows through the whole loop. So I can break the circuit open anywhere. I could break the circuit open here and then complete the circuit with an ammeter. It would be just as well to break the circuit open here, as long as the ammeter is somewhere on that series loop combined with the battery here. We'll use the symbol for EMF and think of this battery as ideal. Yeah, so if the ammeter is on the same series loop as the battery, the switch, and the resistor, then we have the current that's flowing through the resistor. So here's what's important about the construction of the ammeter and the voltmeter. So we recognize the voltmeter has a high internal resistance because that additional internal resistance that combines with the galvanometer's resistance, they're connected in series with each other, which gives a large overall resistance, right? We can say R total for the voltmeter is equal to the resistance of the galvanometer plus the internal resistance, which is typically a very high value of resistance. Okay, so even if the galvanometer itself doesn't have a lot of resistance, the additional internal resistance is large, meaning the total resistance of a voltmeter is really high. And that's a good thing, because I don't want to change the amount of current that flows in my circuit due to the fact that I'm measuring some value for that circuit. In other words, without the voltmeter there, this current flows through the battery, it flows through the switch, and then it reaches this junction. So if the voltmeter had a low internal resistance, then now we've created two paths for current to flow. We've reduced then the equivalent resistance of the whole circuit, and therefore we've changed the amount of current by introducing the voltmeter. That shouldn't happen. So we say the resistance of the voltmeter is very nearly infinite, and so it doesn't really change the overall resistance of the whole circuit. In the same vein, the resistance of the ammeter is very nearly equal to zero. Now why is that? Again, because the internal resistance is connected in parallel with the galvanometer and is a very low value of resistance. And so if we put a very small resistor in parallel with anything, then the overall resistance of this whole device is really small, right? Practically equal to zero. And so if it wasn't nearly equal to zero, then by putting an ammeter in series with the resistor you're trying to measure would increase the overall resistance of the whole circuit, and therefore again it would have changed the amount of current. So we don't want the introduction of the voltmeter or the ammeter to change the amount of current that flows in the circuit. So as long as the voltmeter has very nearly infinite resistance and the ammeter has very nearly zero resistance, then any application of Ohm's law in order to determine the value of this resistor will hold true. However, the resistance of the voltmeter is not truly infinite, it's just some really large value, and the resistance of an ammeter isn't actually zero, it's just some very small value. And so trying to measure resistance of an unknown device is never an exact value. There's an inherent error to voltmeters because their resistance isn't actually infinite, and there's an inherent error in any reading given by an ammeter, again, because its resistance isn't actually zero. So is there a workaround? Is there a way to determine resistance without the inherent error in the readings of ammeters and voltmeters. Well, in our next video lesson, we'll learn about a circuit known as the Wheatstone bridge that provides a workaround. But for now, just know that the resistance of an ammeter is practically zero, and ammeters are always connected in series with the device that they're trying to measure. Voltmeters are always connected in parallel with the device they're trying to measure and have very large internal resistance. Now, wait a minute, am I contradicting myself? Here I'm saying ammeters are connected in series, but didn't I say something earlier about parallel when it comes to ammeters? Yeah, the galvanometer, that loop of wire that's wrapped around this coil that has the needle attached to it that reads these numerical values on the scale. Well, the galvanometer itself has some resistance we'll call R subscript G, and I connect in parallel with that another amount of resistance that I can control. Now, the reason I say I want to control this other internal resistance is because sometimes I want maybe full deflection on this numerical scale to represent 10 milliamps. In other applications, I might want full deflection only represent 2 milliamps or something like this. So by changing the amount of internal resistance that I've put in parallel with the galvanometer's resistance, I can change its sensitivity. In any case, yeah, the other resistor that controls the sensitivity of the ammeter is connected in parallel with the resistance of the galvanometer, but then that whole device is connected in series when I try to determine the amount of current that flows through the circuit. Okay, and again, I'm saying that we connect voltmeters in parallel with the device they're measuring, but when constructing the voltmeter, that resistance of the galvanometer is combined in series with some other internal resistance that's variable so that I can change the sensitivity on the full deflection of the needle. So this in total represents my voltmeter. Yeah, the internal resistance is in series with the galvanometer's resistance, but then that device is connected in parallel with the device that it's trying to measure. Okay, in the next lesson I'll show you how the Wheatstone bridge gets around the inherent errors in the measurements provided by ammeters and voltmeters.